Environments such as this, with tightly packed lots of people and chairs and tables, doorways, visual obstacles that really aren't obstacles, but perceived by the brain as an obstacle will make the legs shut down. So I will tell, people will say, hard to go through doorways. I don't go to the ball game anymore because of all the people, or I go to a party, lots of people, lots of activity, and I just get kind of shut down. So that can be a significant component of this. The brain is very complex, and we still don't understand it yet. As I tell people I work with, I tell my son, Dad didn't build the brain. It's a very complex computer that I don't have a manual for yet, and we're still learning about it as we're trying to treat it. But some very smart scientists over the years have helped us to understand components of walking in terms of the circuitry. And what it kind of comes down to is the framework here, where there will be a sensory input of some sort. I see a stick that I want to step over. I want to go and get the water. That is now on your tables, by the way. A computer of the brain will process that information, and then there will be kind of a multi-component motor output signal that goes together that allows the behavior. So it's very automatic that I want to walk over here. I just take a step, but a lot actually happens in the brain to allow that to happen. There are a lot of circuits involved with this. The dopamine circuit that we've been talking about all morning is involved with automatic type movements. So, without even thinking about it, I just take a step. It just, my posture corrects, and then the start walking mechanism just happens automatically, and I just go. There are non-dopaminergic circuits in the brain that work a little bit more on goal-directed. So I kind of think of it, there's a big stick here. I have to come up with a way to step over it and then keep moving. So there will be a goal-directed kind of cognitive component of that to allow me to move. And then, of course, it gets super complex, and you have all kinds of circuits taking all kinds of information. There's a stick, but there's an angry dog there, so I better step this way as opposed to that way. So all of this works together to give us the correct motor outputs that allow for walking. In Parkinson's disease, the dopamine system, a particular part of the dopamine system, starts to have difficulty, as the group knows. And so some of the automatic components of movement become more difficult. They don't happen the way they used to. And there are a variety of dopamine driven components of Parkinson's disease. The slowness of movement, the stiffness of muscle tone are very dopamine driven. And so we can give levodopa or other forms of dopamine replacement therapy to allow for movements to be bigger, faster, looser, under more control. Tremor involves dopamine and others. So some people notice that levodopa or other medications annihilate their tremor. Doc Hinkle's a genius, the tremor's gone. Other people, what is this guy doing? He keeps pushing up my levodopa and nothing's happening. So there are dopamine and non-dopamine components of that. Same goes for the automaticity of walking. So there are components that levodopa, dopamine replacement, will help immensely, and other components that really don't get to it. And so it is common that in the earlier stages of Parkinson's disease, a lot of aspects of this freezing, start hesitation, getting a little shuffly, are responsive to dopamine replacement therapy. And that seems to be because most of them are driven by the rigidity of the muscle tone, the slow reduced amplitude of movement, and some of this automatic nature. And most of the time people will tell me, my levodopa is starting to wear off, I start slowing down, my tremor kicks up, it's harder to get my feet to move, I get anxious, my thinking slows down, I take my next levodopa, and everything comes back online. The pathological progression of Parkinson's we've already spent some time on, kind of starting in the lower, deeper areas of the brainstem and then moving kind of upwards and outwards. We've been talking, the seat of the dopamine cells that we've been talking about sits here in the high part of the midbrain. It's called the substantia nigra. And those cells are dying slowly over years. You've got tens of thousands of these cells, and it's years and decades that they're having trouble. But when they do die, this part of the pathway starts to have a lot of trouble and maybe not much input in terms of the walking. So freezing of the gait will get worse. As Parkinson's progresses, higher levels of function in the brain will also be affected, and these are areas of the brain that will work on the cadence of gait, posture stability. There's a lot of control of posture and position that has to be controlled before a step is made, or we're just going to go down. And then cognitive changes. There are cognitive components to gait initiation and walking that start having difficulty. And so even some of these non-dopamine pathways can start having some trouble. They don't degenerate anywhere near what the dopamine pathways do, but they can have some difficulty as Parkinson's progresses. In advanced Parkinson's disease, freezing of gait really becomes very non-dopaminergic, hard to treat with medication, therapy, exercise, surgery. Okay, so it doesn't mean you don't do these things, but this aspect of Parkinson's typically does not get a lot better. And unfortunately, this is when people have a high risk for falling and getting hurt. The positive side of this is that there are cueing mechanisms that can be used that our physical therapists are expert at teaching that can help to break the freeze. And there are cognitive, hearing, auditory, visual, and tactile touch components of cueing that essentially feed these systems. Now, this doesn't have anywhere to go, or maybe there's just a trickle, but these goal-directed pathways can still be cued pretty strongly to allow for the movement to occur and to break the freeze. Cognitive cueing, so people will count 1, 2, 3, 4, louder than that if you're working with Melissa. Some people say, I need to relax, and then it will happen. Auditory cueing, metronome, tick, 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 or music. Metallica may not be your thing, but that gets me moving a little bit. But people will find that music will allow them to move around their homes. Having a visual target, kicking a cane in front of you. Stepping over a line is a big one in terms of think about stepping over that line to move forward, or even moving towards a target and thinking about I'm going to that target as opposed to come on, get moving. And then this is John Cleese. So this doesn't happen to anyone either, but people have told me in terms of tactile. If I do one guy told me years ago, it's kind of embarrassing, Doc, but if I do a little wiggle, it'll just break it and I'll go. Or if I step to the side, it'll go. Or if I step back, or if I tap, tap, tap. Sometimes spouses will say if I touch his or her shoulder and say step, that will kind of break the freeze. Vibration, so lots of tactile approaches to this. Whoops, there we go. So this is the video. This is a few minutes long. This was published in JAMA Neurology a few years ago, but it's very, very instructive and very interesting. So I'll be quiet, if I can. So when he counts out loud, the freeze breaks and he can move. Skating movements. So very frozen in place, hard to get the legs to listen. But if he does a different type of movement to the side, he's able to mobilize. So maybe not being able to take that step forward you want, but the step to the side works fine. So very frozen in place. Able to do a different, he was trying to move forward before, now he's just thinking about moving sideways and can do it. There are actually circuits for all of the movement. So a circuit for the side, the circuit for this way, a circuit for this way. And that's, so you can access other circuits to make the movement happen. Oh, I thought that was here. I forgot that was, I thought. And I remember when I was a fellow, there was a gentleman who we'd have to clear out the hallway. He couldn't start walking, but he would fall forward, his leg would kick, and then he could run down the hall. So some people, they have trouble walking, but they can run, or they can swing a golf club, or they can dance. I can dance just fine, but I have trouble walking. And so these automatic circuits are actually used primarily for starting walking, stopping walking, and turning. So those parts of walking become difficult. And so here's a tight visual space, not as cluttered as our space here, perhaps, sorry, but a little cluttered. And then the same gentleman can get on a bike and ride just fine. So when people ask me, can I ride a bike? I say, well, if you can do it safely, yes, wear a helmet, but you can see no trouble whatsoever with the cycling movement of the legs, but then when trying to walk, it just doesn't happen. So different brain, kind of micro circuits that are being triggered for each aspect of this. And this one's even more impressive. So kind of frozen, relax a little to get a step here. And the step over is fine, and then you wouldn't even know this guy has Parkinson's. I heard a whoa in the audience, and yeah, exactly. These are not things I recommend, by the way. My boss is here, so I don't want anyone to do this. Get me in trouble. So kind of stuck in the doorway, just trying to get those legs to move. People say, I just feel disconnected from my legs. I just can't get them to go. I heard an oh my God. I also don't recommend this, but I hear this a lot from people. I can do certain things, others I have trouble with, and I have found ways to get around my house with some, being careful, of course, and with a little bit of creativity. And then just trying to get the legs to move forward is a toughie. And this actually goes back to the pre-levodopa days. People with Parkinson's commented that if they held a ball in their hand and squeezed it, or if they bounced a ball or threw a ball up in the air, it would break the freezing of walking. So it's a tactile cue that kind of allows that motion to happen. This one's also pretty awesome. Not this part. So it's a different, it's up and down steps. It's different than walking per se. And so, a little bit of different neurocircuitry allows for the cadence to be fine and relatively safe. You'll also notice there are lots of different forms here. So everyone has their own, their own experience with this. It doesn't usually get this bad. And that's the same gentleman running up and down the steps, no trouble, well, little trouble. Okay. And then you can subscribe if you want, but you don't have to. All right. Thanks, guys. So we do have ways to try to help people cue. One of them, several of you have seen in our office. We have, this is a U-step walker designed by an engineer for his mother who is having freezing to gait issues. It will give some cues, but it's pretty heavy, pretty bulky, pretty tough to use in the house, which is why we got one for now 5 at clinic to let people try it. Some people say, wow, this is awesome, and some people say, I'm glad I didn't buy it. This is awful. And the eyes are directed down. A lot of the technology that's available now to buy has people looking down to step over things, and they're not looking up and interacting with their environment. So the future of cueing therapy really needs to be multimodal. It needs to involve auditory, visual, maybe tactile, multiple things that are small, wearable, and personalized, because everyone has their own cue or group of cues that allows them to walk. My son Brett and I, who some of you have seen before, he's now, when he was first introduced and taking water around, he was this tall. Now he's taller than I am and lets me know it. He and I are going to work on some augmented reality, which is glasses where you can still see your environment, but then we'll throw up a visual. So a few people in this audience perhaps followed me as I walked around the clinic with a laptop. The research people, you didn't hear this part, but I'm walking around. I didn't have approval to do this, and they would watch the screen with the step, 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 step. Some of them said, I think that's kind of helpful, I'm not sure. With the idea that maybe in glasses you have something that would give a visual cue that allows you to be up, looking at your environment, and having an external cue guiding you through it. We can put a little auditory tied to it, and we would also do this. Again, research people, don't listen to this part. And so in addition to the visual, a sound, and I'd walk around like this, and so tap, 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 tap. And so I tried to take a few out of these because I thought it was a little long, and it is, so I'll get there. There we go. So a few people, not scientific study, by the way, but a few people said, you know what, when I see something with the sound, or maybe just the sound alone, it was actually kind of helpful. I could get through that doorway a little bit better. We could negotiate the hallways a little bit better. And that's all fine. The problem still remains, though, detecting freezing of gait. So when does that turn on? Is someone going to walk around with this happening all day long, or pop, pop, pop all day long? That's not going to work. So how could we detect freezing of gait as it's developing before it becomes a fall? And so this is where the Dr. Contag, sorry, I'll get it. Part of the talk will come in is very, very exciting. If we could, in some way with a wearable, diagnose a freeze in the early stage and then throw a treatment through glasses, through sound, through tactile within the garment, that might be a way to diagnose and treat and prevent the freezing event and therefore the fall from happening. One of the problems that develops that becomes very intrusive, that really requires the treatment component, is that as Parkinson's progresses, many folks tell me their thinking is slower than it used to be, harder to get words out, harder to multitask. And so the idea of whoops, I'm freezing, I'm going to grab that, or whoops, I'm freezing, I'm going to stop and protect myself, happens too late, and the fall may already be initiated. And then if dementia starts to develop, more significant cognitive problems, I have lots of spouses in the office that say, I'll walk with my wife, and when I notice she's starting to freeze up, we'll tap the shoulder, or we'll do the cues, pick up your feet, take a big step, and we can't have a person with us 24/7. So if we had something that could automatically detect, diagnose, and then automatically give the cue, that would be wonderful. So my colleague now, Chris, will come up, and he's got a long title, Chair Department of Biomedical Engineering at Michigan State University, so not as bad as Michigan, right, guys? So it will be nice, but he is doing, we had a nice dinner last night, he is doing incredible work on multiple levels that could be helpful, but he and I have established an early collaboration to see if we can do just what I was bringing up. And why don't you come on up and show them what we got so far and what we're thinking.
Good to go? Great, thanks. Thank you, Dave, for the introduction, and thanks to all of you who have welcomed me to your extended family to be a part of this meeting today. I'm going to start out with a confession. I've never, ever given a Parkinson's disease talk before. But I've been interested in Parkinson's since very early in my life. As a 10-year-old, I was helping my grandmother with Parkinson's clean out her storeroom. And we happened upon this trunk. And as a 10-year-old, to me, it looked like a treasure chest. It had this humped back, and it was just this beautiful trunk, and it was obviously very old. And I was cleaning up the storeroom, and I said, Grandma, what's that trunk? And she said, let's sit down. So we sat down, and she told me the whole story about that trunk. It was purchased in Wales by my great-great-grandmother, and as they followed Brigham Young to the Promised Land, it came across the Atlantic on a sailing ship, and then it was on a covered wagon, went to Utah. And then when my great-grandparents left the Mormon church, they threw the trunk again in a covered wagon and took it to Idaho. And my grandmother then packed in it to go to college at Iowa State, where she learned to be a teacher, and it followed her to Minnesota, which is where we're having this discussion. A few years later, just before my grandmother passed away, I met with her, and she gave me an envelope. I said, what's this? And she said, open it. So I opened this envelope, and in there was a note from my grandmother that she'd written with her tremor of all the people who had owned that trunk since the beginning when it was purchased in Wales, and my name was the last name on that list, and she said, I'd like you to have this trunk. So it sits on the floor of my house with that piece of paper still in the bottom. And every day I walk by, I'm reminded of the fact that she suffered from Parkinson's. When I went to graduate school, I studied a neurological disease caused by two viruses. These two viruses would interact together to kill motor neurons in the spinal cord, and it was a mouse model of Lou Gehrig's disease, or ALS. At the time I was doing these studies, we learned that HIV would also go to the brain. So when I went to Stanford to do my postdoc, I studied the transmission of viruses into the brain that would lead to the dementia associated with HIV. Some of the same or similar barriers to the virus getting across the blood-brain barrier are present in the placenta. So I also studied mother-infant transmission of HIV. The way we did that was by taking as many viruses as we could from as many different places and sequencing them. HIV mutates so frequently that every virus in the body is different. And the idea was that if we could track the signature of that genome through the body, we could then figure out where that virus came from that was transmitted to the baby or that got into the brain. It was at that time I said, wouldn't our lives as scientists be so much easier if we could watch these infected cells move in the body? So I started what I thought was a little project that turned into a 25-year tangent in my career to develop imaging tools. We created a tool that would make mouse models of human disease transparent for scientific investigation. We take genes from places like fireflies that you see in your backyard, put them into cancer cells, stem cells. We put them into immune cells, and we could watch these cells based on the light that went through the tissues. If you take a flashlight and put it behind your hand, you know that light goes through the tissue, and that's what we use to track these infections. That led to a company that eventually hired a friend of mine by the name of Vivek Shinde Patel. And Vivek was at our institute, and he said, you know, I've really enjoyed the commercialization of the tools that you developed at Stanford, and I'd like to do something different. And I said, here's what I've been thinking. We have the ability to create soft robotics or artificial muscles. We have the ability to sense muscle function. Why don't we combine those into an exoskeleton, not a big bulky one or not one that looked like Iron Man, but rather a nice suit that would give support and also sensing capability. We were doing this in the Institute, and let me talk a little bit about the Institute because it's kind of a unique place. Like I said, I left Stanford to start this institute, and we set up 8 different thematic areas that were on the 4 floors of this building. We heard about the genetics of Parkinson's earlier today, and I did take notes during your talk. I labeled my notes Parkinson's Gospel, according to Dave. So I know you said it was take it with a grain of salt, but I learned a lot through those discussions today. But on this floor, the first floor, we have a group of people who were able to predict human height from your genome. We know if you look at your kids, you look at your parents, you know height's heritable. And we've had the human genome sequence for 20 years, but nobody's been able to predict how that genetic transmission of height occurs. We heard about Parkinson's, the 8 or so genes that can be looked at using genetic tests. To predict human height, we did an array of 800,000 markers and had to use 20,000 markers to predict human height. Complex diseases result from a complex constellation of genes. So we've applied that same algorithm to osteoporosis, kidney disease, breast cancer, and can predict many of those diseases by looking at hundreds of thousands of markers, not a handful. We have a group on the second floor, we have a group on the second floor of this building that is coating neural electrodes with diamonds to try to improve the interface between the brain tissue and the electrode. And also looking at the different architectures. Are electrodes with holes better than solid electrodes? Because we know that there is an interaction between those materials. We have a group developing new imaging tools, and you heard about the imaging of radio-labeled dopamine and dopamine transport. We have a whole range of isotopes that we're developing. We built a new radiopharmacy on the backside of this institute to develop new tracers for neurological diseases and cancer. So we see our institute as a place where we do first ever to first in humans. One of the other first evers that I find is just a great story is insects can smell amazing things. And so we put those diamond electrodes and other electrodes into the brain of the insect and ask if they can sniff cancer. They don't just say no cancer, cancer. They say cancer of this type, that type, that type, and that type, and identify the pathways that are dysregulated that we can go in and intervene with. So first ever to first in humans. And one of the things we've been trying to then translate into clinical studies led to a company that, I'm going backwards, so sorry. Led to this company called Exoforce. And the idea was to create an exoskeleton, a soft robotics exoskeleton with built-in sensors. And Vivek has really been spearheading this. And I have to admit, I'm more of a cheerleader than actually one of the drivers of this technology. But Vivek was here working with Dave on the ability of using this for freeze of gait. So there's a variety of things that we can build into these suits. The electronics and the advances that we've made in sensors and detectors are incredible. We started with EMG, or electromyography, asking, can we sense what the muscles are doing? We can build in other indicators of overall health and wellness, and of course, drive interventions, which is what Dave was just talking about. So this is the suit worn correctly, and this is the suit inside out. And these are the sensors that run along the suit, and there are electronics that can then take the signals from the muscles and interpret them. And we've been working on artificial intelligence to try to interpret them faster, better, and more accurately. We developed this, both pants and arms, and we've started now developing with the heart monitor for some of those vitals that we were just talking about. So we asked, with Dave's help, can we use this for detecting freeze of gait? So EMG is not a new technique. It's been around for a long time. In the early days, they put needles into the muscle and measured the electrical pulses. That moved then to wearable or surface electrodes for EMG. And the technique or the technology has gotten smaller and smaller as we move forward, to the point where we have very small electrodes and readouts. And these are some images I've taken from the web. This isn't our work, just have to apologize in advance. But you can have the readout on your cell phone so you can see what your muscles are doing. Muscles active, inactive, active, inactive. And this can all be detected in real time. So here's an example of measurements made with the electrodes built into the garment versus electrodes that are on the skin surface, a more conventional clinical power lab. What we asked the normal volunteers to do is to lift up barbells, 1 pound, 2 pounds, 3 pounds, and of course, as the weight increases, the amount of energy takes to lift that weight increases, and you can see that in these readings. We can also watch muscle fatigue. So we can ask the normal volunteer to do curls, and then do curls until they can't do it anymore, till they fatigue. And we can track that muscular activity, and then rest and muscular activity again, and this is that fatigue stage. So we can tell when the muscles are working, we can tell when they're tired, we can tell when they stop working. Seemed like a perfect way, or a great way, to really understand freeze of gait. So with help from a patient who was willing to work with us on this, we put the sensors into just the garments on the lower legs, and just asked, when you go through a doorway, do you have a freeze of gait, and can we detect that? So we see muscle activity, freeze of gait, muscle activity, freeze of gait, muscle activity, freeze of gait. And those of you that go through this probably understand what this feels like, but now we can watch it as this individual is going through the freeze of gait. And we looked at here the 3 of those freezes. So if we zoom in on those patterns, the muscle activity patterns, we watch the muscles work as the individual's walking, and then just before the freeze of gait, we see signals that indicate that the muscles have stopped working. That gives us 3 to 4 seconds, which in computer time or AI is like a lifetime. We have the ability to deliver a signal. Either the signal says, grab onto something, you're gonna freeze, or the other tactile sensors that Dave's been talking about are visual cues. So that's been the goal of these studies. And then eventually to use that to drive soft robotics. This is work from Jinsing Lee's lab. We recruited him out of Stanford, where he was developing soft robotics. The guy is really incredibly creative. If I could list all of the things he does, it'd be tremendous. But he works on soft robotics, and this shows you what you can get these artificial muscles to do. So if we could build these into the suit, into the garment, so that when the freeze of gait's about to happen, A simple thing would be just to vibrate, but maybe we need to grab and support the muscles that aren't working. And we would try to mimic the musculature of the legs so that we could augment the muscles. So we talked about augmented reality. This is augmented strength. We think we can increase the strength by about 20%. Again, not like Ironman, where it's 1,000-fold increase, but just a little bit of support so the person doesn't fall. We thought this was a good idea about two to 3 years ago. And a friend of mine told me, if you have a good idea, don't worry, someone's already had it already. So as I was preparing for this talk, I ran across this article that was written for the popular press. It was published in Nature Medicine. But a group at Harvard had built in soft robotics. These are the soft robotic artificial muscles with attachments at the knee. And they were able to, in the study of this one patient with freeze of gait, they could show that there was an improvement in that ability to walk and avoid freezing of gait. So what we'd like to do at the company is to begin to use EMG to guide this soft muscle, the soft robotics and these artificial muscles to take us to the next phase. So this is Vivek, again, a friend of ours. He actually did a postdoc with Anna Moore, who's also a faculty member now at MSU. Anna had been at Mass General and Harvard for 27 years, and she flew out yesterday to go give a talk at AACR about her cancer therapy to prevent metastatic breast cancer. She and I and Vivek started the idea of ExoForce, and then we recruited Leslie, who is a scout for the Jacksonville Jaguars, to think if you can use this for freeze of gait, you could use this for other applications as a training tool or to prevent fatigue, prevent injury. And so she's been working with professional athletes and also special forces on how these tools can be used in those environments. Ron has experience on Wall Street, and he's just this tremendous library of knowledge, and so that we've all teamed up to create this company, ExoForce. My day job is running this institute. And the people who have really done the work I talked about today are the people that I showed on the last slide, and of course with Dave's help. And I see myself more as a cheerleader for that company, but the idea originated through Vivek and I having a conversation. When we started IQ, we call the Institute for Quantitative Health Science and Engineering IQ. This is an old picture. Actually, now we have an IQ on the top of this building. We said we wanted to work in a building with a high IQ. We wouldn't want to label it just down low at the door. We wanted to make sure it was really high on the building. And we think our goal is to develop the tools, technologies, and knowledge that will ensure 100 years of health for all people. Not 60 years of health and 40 years of health problems, but 100 years of health. So with that, I'd like to thank you for your attention. And again, thank you for inviting me to come up and speak.